Okay, this is Math Analysis Honors, and we're looking at Chapter 13.5 and 13.6, which is conditional probability and binomial probability. So we're going to start with conditional probability. Conditional probability is when you know some information about what's going to happen. So generally what we're going to be looking at is the probability that one event is going to happen if we know that the other event has happened, or if we know some condition. So the probability of A given B is that probability that they both happen, A and B, over the probability that event B is going to happen. And because of the fraction here, we can't have the probability of B equaling 0 or cannot equal 0. Otherwise, the fraction would be undefined. So what this means is the conditional. This is probability of event A given event B has occurred. And so that's what this means. So the probability of event A given, that's what that line means, the probability that event B has occurred. So, for example, Vanessa tosses 2 coins. What is the probability that she has tossed 2 heads, given that we know she has tossed 1 heads? Alright, so the probability of tossing 2 heads, that's our A. That's the event that we want to know what happened. And the probability and we know that she's tossed at least 1 head, so that's our given B. So the probability of 2 heads given the probability given that 1 head, the first is heads. No. The probability that there is at least 1 heads. Alright, the way I would approach this one, a good way to sort of illustrate this, would be using our tree diagram. Alright, so we have our first toss and we have our second toss. So the first toss, obviously you have 2 options, heads or tails. Then from there's 2 options for the second toss, heads, tails, heads, tails. So we know that she has tossed at least 1 heads. So this would be at least 1 heads, this would be at least 1 heads, and this would be at least 1 heads. So the probability of at least 1 heads is equal to 3 out of 4. Because there are 3 out of the 4 of them that have at least 1 head. The only one that doesn't is the tails right here. Alright. Now the probability of 2 heads and at least 1 heads is the probability that she has 2 and has at least 1. And the only situation that would fit both of those would be this one right here. Alright, because that one has 2 heads and it has at least 1. So for that would be 1/4. Alright, so our probability of 2 heads given that at least 1 heads has occurred would be the probability of both, so that would be the probability of A and B, which is 1/4, over the probability of B, which is 3/4, which is 1/4 times 3/4, which is, 1/4 times 4 over 3, because we multiply by reciprocal, 4's cancel, which is 1/3. So you find the probability that both events happen at the same time, and you divide by the probability that the given event happens. And that's what I did here. So the probability that both events happen is 1/4, because that's 2 heads and at least 1 heads. And then the probability that you have at least 1 heads is 3/4. That gives you the probability of both of them together. Now this one here is actually a special case. All right, because in order to have 2 heads, she has to have at least 1 heads. So in this situation here, we're going to go down to the, oops, what happened here? Well, technical difficulties. So in this case, event A is a subset of event B. So if we think about all the possible outcomes, if event B is at least 2 heads, at least 1 heads, the only way to get 2 heads is to have at least 1. There's no way to get 2 heads if you didn't have at least 1 heads first. So in this case, event A is a subset of event B. So in this case, let's write that. In this case, the probability of A and B, the area where they overlap, is only the area of A. So the probability of A and B is just A, so the probability of A given B would just be the probability of A divided by the probability of B. And so this is like example number 1. Let's try a different example. Vanessa tosses 3 coins. What is the probability that she has tossed exactly 2 heads, given that she has tossed at least 1 heads? Alright, so again, I like to draw the diagram. So we have 3 tosses. 1, 1, so 1, 2, 3. So on her first toss, she can have heads or tails. On her second toss, again, she can have heads or tails. And on her third toss, again, heads or tails. Alright, so in this case, there are 8 possible outcomes. This would be heads, heads, heads. And this would be heads, heads, tails. And so on and so forth. Alright, so we want to know of all of these different outcomes, exactly 2 heads, and we know she's tossed at least 1. So the exactly 2, so let's start with, so the probability of exactly given at least 1 would be the probability of 2 and 1 over the probability of just 1. That's our event A and our event B. So if we look, first of all, the probability of 2 and 1, and then the probability of just 1. So let's start with all the possibilities that are just 1. So this would be here, it's just 1 heads. Here is at least 1. So here, 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 and then all 4 of these, because the first one was a heads. Alright, so there are 7 out of the 8. Now this is another situation where in order to have 2, you have to have at least 1. So event A is a subset of event B. which means that in order to have 2, you already had to have 1. So in this case, that would be this one here has exactly 2. This one here has exactly 2. And this one here has exactly 2. Alright, so that would be 3 out of 8. And so then the overall probability would be 3 out of 8 divided by, which means times the reciprocal of 8 and 7, which would be 3 over 7. I know this works a little messy. I hope it's not too hard for you to follow. So in this case, and this happens often when you have repeated events. Again, one is a subset of the other. All right, so our last example, 12-sided die has numerals 1 through 12 on its faces. The die is rolled once, and the number on the top face is recorded. What is the probability that a number is a multiple of 4 if it is known that the number is even? So, we want, what is the probability of a multiple of 4, so that's our event A, given that it is even. That is event B. So the probability of the multiple of 4 given we know that's even. Alright, so that would be the probability that it's a multiple of 4 and even over the probability that it's even. Alright, well, if we think about all the numbers 1 through 12, and if it helps you write them down, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's start with the probability that the number is even. Well, there are 1, 2, 3, 4, 5, 6 numbers that are even. Alright, so that would be 6 out of the 12 numbers are even. The probability that is both a multiple of a 4 and even, well, 2 is not, 6 is not, and 10 is not, but 4, 8, and 12 are multiples of 4 and even, would be 3 out of 12, which is 1/4 and 1/2. So this would be 1/4 times 2 over 1, which is 1/2. That's a 2. Alright, so that looks like a 3. It's actually a 2. Alright, so the probability of that occurring, that if we know it's even, the probability it's multiple of 4 is 1/2, which would be the answer. Use the formula and hopefully you won't find that to be too complicated. The next thing we're going to talk about is binomial probability. This is when you have a repeated event that can only happen in one of 2 ways. Alright, it's very important that this only has 2 outcomes. Alright, so true or false, heads or tails. It has to be something that has 2 outcomes. So there's an example of this, and we're going to solve this example in a minute. 8 out of 10 people who contract a certain viral infection can recover. Alright, and I assume this means can recover without going to the hospital, will not die. If a group of 7 people has been infected, not infects, has been infected, I apologize for the typo, what is the probability that exactly 3 people will recover from the infection? Alright, so there are essentially 2 outcomes here. Either you recover or you don't recover. Alright, 8 out of 10 people do recover, which means 2 out of 10 people don't recover. Alright, so the binomial experiment is when a repeated event has only 2 outcomes. Either you recover or you don't. Alright, so the conditions for this are each event has 2 outcomes or can be reduced to that. Alright, so for example, maybe there's more than 2 possible outcomes. So you define some of those as success and some of those as failure. Then that would be your 2 outcomes. Your 2 outcomes are either success or failure. You have to have a fixed number of trials. Alright, so that means that there are 7 people who've been affected. Or I'm going to flip the coin 12 times. But there has to be a finite number of times. Each trial is independent. All right, so there can't be there can't be any number of each trial can't affect the one that comes after it, and the probabilities must be the same for each trial. All right, if you find yourself in a situation such as this, then there is an easy way to calculate the outcome of a certain number of trials. So the probability of event A, of exactly a number of certain outcomes of n number of trials is the combination of the total number of trials and the number of outcomes you're looking for times the probability of success raised to the power of a times the probability of failure raised to the power of n, I can do it again, n minus a. So essentially what this means is, let's say I want to know with the flu virus that 3 of the people will recover. Well, if 7 people are infected, that means the probability of success is 3, and the probability of success would be the 8 out of 10, so it would be 0.8, and the probability of the failure would be 2 out of 10, or 0.2. And remember that the probability of success plus the probability of failure always has to equal 1. So let's go to the example above. Alright, we want to know the probability that 3 people recover. And we know that the probability of success or recovery, hold on. Okay, so the probabilities of success or of recovery, so let's say the probability of recovery is 0.8, which means that the probability of remaining infected or failure would be 0.2, because those two have to equal 1. So the probability that exactly 3 people recover is the probability of a combination of, out of the 7 people, 3, which is using our combination formula. The success, or the recovery, would be 0.8 to the 3rd power, and the number of failures, since there were 7 total, would be 0.2 to the 4th power. Those two exponents should always equal out the total, because if there's a 0.8 chance of success, then there's a 0.8 chance times 3 that we have a success, and if there's a 0.2 chance of failure, then there are 0.2 times to the 4th chance of failure. Alright, which is, the combination would be 7 factorial over 4 factorial 3 factorial times 0.8 to the 3rd power times 0.2 to the 4th power. Of course, you'd need a calculator for this, which would be 7 times 6 times 5, the 4 factorial cancels, over 3 times 2, which is 6, times 0.8 to the 3rd times 0.2 to the 4th. And so that is the point that we have an answer that is calc ready, 35 times 0.8 times to the 3rd times 0.2. So I get myself a calculator, and I've got 35 times, parentheses, 0.8 8 to the power of 3 times 0.2 to the power of 4. If I hit enter, so it would be 0.0286. So the probability is 0.0286, or a little more than 2%. And that's good because there's a pretty low chance that 4 people remain infected, because most people, 80%, are going to recover from the illness. There's a trickier way that we can ask this question, and that's what if at least 6 people? Well, at least 6, so the probability of at least 6 is the probability of 6 people plus all of the numbers that come above that. So if there were 10 trials, then that would be 6, 7, 8, 9, and 10. In this case, there's only 2, so it would be probability of 6 plus the probability of 7. So the probability of 6 is, out of the 7, we choose 6. You can write it this way if you prefer. Times 0.8 to the 6th power times 0.2 to the 1 power, because there are 6 successes and 1 failure. And the probability of 7 would equal 7 choose 7, which is just 1, times 0.8 to the 7th power times 0.2 to the 0 power, because remember, all those numbers always have to add up to 7. Alright, so this is 7 factorial over 6 factorial, 1 factorial, which is just 7, times 0.8 to the 6th power times 0.2 to the 1 power, and this is 7 factorial over 7 factorial, which is just 1, times 0.8 to the 7th power times 0.2 to the 0 power is 1 again. So I go to my calculator here, and I get approximations. So I have 7 times 0.8 to the 6th power times 0.2 to the 1 power, which would give me 0.367, 0.367, and then I have 0.8 to the 7th power, which gives me 0.209. And if I add them together, and remember, you can copy and paste, so scroll up here. So choose that one, enter, plus, choose the one above it, enter, 576, or 577. So 0.576. So there's better than a 50% chance that they will all recover. So that's called the binomial experience. You have the rest of the period to work on your homework. Good luck with that.